Hi, and welcome back. This video is sponsored by FabFilter. Regular viewers might think that's odd. Why didn't I make the video for their channel, as I regularly do? Well, we did consider that, but I wanted to be able to test analog model plugins, as well as just the FabFilter offerings, and go into lots of geeky technical detail when required, and we decided it will fit better alongside my usual content. But the FabFilter team provided me with a list of common customer support questions they get asked regularly, and requested a video that addressed them properly, which they could then refer people to. So this video will be a mixture of those, plus some of the worst plugin doctor fails I've seen from fellow YouTubers, and some guidelines as to how to actually make meaningful measurements, and just as importantly, how to interpret the results. I'm going to start with the gold standard of audio tests, the Null Test. This is one of the few tests that can give us a definitive yes or no answer. But it's an answer to the question, are there any differences between these audio signals? It doesn't address the follow-up question, are those differences actually audible? Here's a sine wave test tone, which I've rendered as an audio clip. And below it is an identical copy, which I've flipped upside down, so the positive halves of the wave are now negative, and vice versa. If I play both these clips together, they cancel each other out, and we just get silence. This is what we call a perfect null. Before I turned it upside down, the lower sine wave was identical to the upper sine wave, so they're now equal and opposite, and the sum of the two waves is always 0. This also works with more complex signals. Here's a clip of pink noise, and an identical copy flipped upside down. Add them together, and they cancel out. And of course it also works with any other audio, like a full stereo mix, for example. This time I've flipped the polarity on the channel instead of for the clip, so we don't actually see the waveform upside down, but it's the same thing and it has the same effect. Total silence when both are in together. We can still see the meters bouncing for each channel, but the mix bus, where they're added together, has dropped to silence. So, how is this useful? It can answer a couple of different questions. First of all, is this plugin transparent when it's not doing anything? Here's an instance of Pro Q3 with no EQ bands enabled at unity gain. It's claiming to be doing nothing at all, but is that actually true? It's easy to find out. Let's turn on the inverted copy again, which isn't running through Q3, and there's a perfect null again. So we can be absolutely certain that when Pro Q3 tells you it's not doing anything, it really isn't doing anything. And yes, I do mean absolutely certain. I've seen people claim that two files can null perfectly and yet still sound different. And I have to ask, how? A perfect null is proof that every single sample is identical in both files. There's nothing else in digital audio, it's just the numbers. If the numbers are the same, it sounds the same. And if you don't accept that, you're watching the wrong YouTube channel. Try crystal healing or homeopathy or one of those audiophile hi-fi channels instead. So let's counter that with an example of a plugin that fails that test. Fails being in inverted commas because it's by design and can't really be considered a flaw. Here's the Marg EQ4 from Plugin Alliance with all bands set flat. And this one doesn't null completely. There's quite a lot of signal still on the master. As with many desirable pieces of analog hardware, the Marg EQ appears to have some box tone, meaning it colours the sound slightly just by being inserted into the signal path and before you've actually done anything with it. And the plugin recreates that box tone and likewise changes the sound a little as soon as it's loaded. The Null Test confirms this fact definitively and unarguably, but it can also provide some insight into the nature of the difference. If we look at the different signal with a spectrum analyzer, we can see where the differences are. If the difference signal is mostly low frequencies, that means the differences are greatest in the low frequencies. Just to prove the point, let's boost the low frequencies with the Marg EQ and deliberately introduce some larger differences. And suddenly we get tons of low frequencies in the difference signal. Note, however, that this test doesn't tell us much about the nature of the difference. If I cut the low frequencies instead of boosting them, The effect on the difference signal is much the same. We also can't infer very much about how audible the difference is. Yes, the difference signal increases as the differences increase between the two signals, but it's showing us the mathematical difference, and our brains are more complex than that. Some differences are more important than others in terms of audibility. Here, for example, is some hard, nasty clipping, brutally smashing off the loudest peaks of this mix in a way that's quite audible and noticeable. If I null test this, we hear brief bursts of signal for the clipped peaks, but the rest still cancels perfectly. The null test says this audio is 90% unchanged, but our ears tell us it's kind of ruined. Contrast this with an all-pass filter. This is the filter that doesn't change the frequency response at all. It just shifts the phase 180 degrees at the target frequency. I'm not going to say that this kind of phase shift is always inaudible. Perhaps you do actually hear a difference when I toggle bypass. But I am going to say it's usually inaudible. And just to prove the point, I'd actually switched the filter in and out several times behind the scenes before you saw me toggle it, and I bet you didn't notice. Alright, let's null test this one. And look at the huge difference we see on the master channel now. Checking it on the analyzer reveals that in fact we've created a bandpass filter. The frequency that is flipped by 180 degrees by the all-pass filter no longer cancels out. In fact, it's back in phase with the inverted signal we're trying to null it against, so this frequency is actually boosted in level. The null test tells us this is a huge and significant difference, but our ears don't really care about it at all. The complexity of our hearing is another reason to use null tests. One of the most important ways we learn to trust our ears is by learning when not to trust them. This is a subject that can sometimes rub people up the wrong way. I'm not saying your ears are bad. Quite the opposite, in fact. So let's pause a moment to talk about cognitive bias, but from a slightly different perspective. That music we've been listening to, what do you hear when I play it back? There's drums, right? You can probably hear a bass part, unless you're listening on your phone or something. And there's a piano and a guitar. 4 separate parts, counting the drums as one. Except you weren't hearing 4 separate parts, you were listening to one waveform. Or, if you're doing me the honour of listening in stereo, 2 waveforms for the left and right channels. All that separation into individual parts happens entirely inside your head. Think for a moment about the incredible processing required to achieve that. I mean, we can sort of do it in software these days. There are tools which claim to be able to separate a mixed file into separate components like drums, bass or vocal. But as impressive as these tools can be, they can't yet do it as well as we can when we just listen to a mix. Now think about this. Imagine you listen back to a mix on a good system with plenty of detail. Let's imagine it's a reference mix rather than one of your own to avoid complications. You listen properly, focusing on all those little details that the good system can reproduce accurately, and you reach the end of the song. Okay, great. Now, without moving from your seat, you use your phone or your remote control or whatever to play that same mix again. Nothing changed. You haven't even moved. You're going to have a different experience the second listen. You'll notice details that you missed the first time around, and in focusing on those details, you'll miss things you did hear the first time around. This is a feature of your massive, complex, sophisticated brain. Not only can you separate the different elements of a mix in your head, you can focus on and, in effect, magnify the details that you're interested in, while suppressing and minimizing details you don't care about. We can do this so well that someone with musical training can listen to a fully mixed song and transcribe all the parts for each instrument with a reasonable degree of accuracy. Indeed, 3 years of my own career was spent as a full-time MIDI programmer doing precisely that. Okay, now imagine you did exactly the same thing. You listened to the same mix twice, back to back. But this time, you know something has changed. Different interconnects, different speaker cable, magic audiophile pebbles aligned with ley lines, whatever. Suddenly, all those differences in your experience of that mix have a logical explanation. It must be the magic pebbles, right? This completely normal psychological effect is called a cognitive bias, which presents it as a negative, a failure to properly interpret the incoming data. But I don't think we should think of it that way. Rather, it's the consequence of that awesome, mind-blowing power we have within our heads to deconstruct that composite waveform into its component parts and recognize which harmonics belong to which fundamentals, and to do it all in real time without conscious effort. If we lacked that ability, would music even exist? But it does mean that it's impossible to separate our perception of what we hear from other stimuli, such as what we see on screen, what we feel when we operate real analog pots, even perhaps what we smell when powering on old valve gear. When differences get subtle enough, sometimes we need a null test to tell us if they even exist at all. As an extreme example, this all-pass filter running in Volcano 3, it's set to the clean style, so it's totally linear with no saturation or distortion. It should, in theory, be identical to the all-pass filter in Re-EQ, Reaper's stock EQ plugin. Given that we can't hear any difference between filter in and out, at least I can't hear any difference, we can't hope to judge this by ear. But the null test can answer the question definitively, and it's a yes. No difference at all once the peak and bandwidth settings are matched. But look what happens if I switch to the other filter styles. It's definitely not nulling now, telling us that the filter saturation is still significant even with the all-pass filters. And also that the saturation is significantly different for each style, as the difference signal changes audibly for each. But when we get back to clean, no difference again, they're exactly the same. And that's not a matter of opinion, it's just maths. A quick aside before I move on, Reaper provides a built-in null checking feature, which will subtract the processed signal from the input signal and play you the difference. Right-click the dry-wet mix knob at the top right of the interface, and you'll see a delta solo feature. With no bands enabled in Volcano 3, the result is silence, so a perfect null. No change at all. But if I enable this all-pass filter again, there's that bandpass filter we had earlier. So that's the null test. Very useful as a sanity check to tell you if you're imagining a difference when there isn't actually any, and also useful if you want to match the curves between two different equalizers where perhaps the Q values aren't stated, or use a non-standard definition of Q like the fab filter, or perhaps are expressed in terms of bandwidth instead, like in Re-EQ. Alright, I'm going to stick with the subject of EQ for now, and let's talk about some other ways to measure it. If you're a regular visitor to this obscure little audio production corner of YouTube, you've no doubt seen people, including myself, using an application called Plugin Doctor to test plugins and see what they're actually doing. Plugin Doctor is made by DDMF and is priced very reasonably, making it accessible to consumers as well as plugin developers. But of course that creates a problem. While the tests that Plugin Doctor offers are valid and useful, it's also important to know how to use it properly and how to interpret the results. Here's what you'll first see if you load ProQ3 into Plugin Doctor. We're on the first tab called Linear Analysis. More on this in a moment. And this shows us the frequency response of the plugin. As you might expect from a modern, perfect EQ like this, Q3 is completely perfectly flat until you actually dial in some EQ. And whatever curve I create in the plugin, it's mirrored exactly in the analyzer a fraction of a second later. This is reassuring, but perhaps not surprising. This test becomes more enlightening when you're testing a more analog-style EQ, which might include some quirks modelled from the hardware. Like the Marg EQ we looked at earlier, for example, the knobs are all set flat. I'm not cutting or boosting anything, but the frequency response is already subtly altered. This isn't a flaw, of course, it's intended behaviour and probably part of the reason you're using this instead of a more digital-style EQ. But there's no indication of what is happening on the plugin interface. Your ears may tell you the sound changes just by loading up the plugin, but if you want to understand exactly how it changes, Plugin Doctor is very useful. Of course, some people might sneer at this, saying that it doesn't matter what it looks like, you need to judge the sound using your ears. This is true, of course, but our ears are all fallible. I don't care how good yours are, they can still be fooled. Here's another plugin. This one models the preamp and EQ of a classic console. The most obvious thing about the frequency response is this big bump here, but that's actually 30 Hz and won't really affect most sources much. A non-negotiable high-pass filter, tuned down low like this, suggests they've modelled a transformer input or output stage, as well as just the EQ. For most of the audible frequency range, however, the response is commendably flat. But it's not at unity. There's a boost of over 1 dB for the whole frequency range. This is easily enough to fool you into thinking there's a desirable box tone, when in fact it just got louder. A better starting gain setting for this plugin, in my opinion, would be something like this. Now most of the audible frequencies are at unity, and never mind that 30 Hz boost, it'll probably only affect the kick channel. If the plugin, or your DAW, allows you to set a custom default preset, you should definitely set it to give broadly neutral unity gain with flat settings. It will make life a lot easier. Another thing you might want to test for is EQ cramping. Here's Pro Q3 boosting 1 kHz with a bell-shaped band. And here's Reaper's stock EQ doing the same. And the results are almost identical. Now let's try boosting 10K instead. And there are big differences now. Re-EQ's bell is now narrower than it should be. I can compensate this to an extent by adjusting the width of the bell in Re-EQ. But notice this only works for the lower half of the bell. The upper half always plunges down to unity at the Nyquist limit, which is half the sample rate, giving us an asymmetric bell shape. This is all quite obvious and easy to see with a modern digital-style EQ like this. But what if you're testing a model of a vintage EQ, like this anonymous Pultec emulation? How do you know whether the high-frequency boost is cramping out of shape, or if it's correctly modelling the quirks of its analog counterpart? The definitive test is to change the sample rate. If the EQ looks asymmetric at 44.1 or 48 kHz sample rates, but becomes more symmetrical at higher sample rates like 96 kHz, then this is indeed cramping. Of course, cramping doesn't make an EQ plugin useless. It will only make a difference up at the very highest frequencies, and even then the difference might be insignificant. But such a plugin might benefit from 2 times oversampling or a 96K project sample rate when running high-frequency air boosts, and this is useful information. Okay, these are all useful, valid tests so far. Let's look at an example of a useless, invalid test instead. I'll load up another classic EQ plus preamp model, Neve style this time. This one provides a choice between line or mic preamp input stages, so we should be able to see how the frequency response changes when you drive these hard, right? The plugin I'm testing actually has stepped controls, so I'm going to increase the input gain 1 step at a time, while decreasing the output gain in the same way. And let's see how the graph changes while also listening to those same settings applied to a drum bus. That's the mic input. How about the line input? Can we agree that the graph display bears no resemblance whatsoever to the sound we're actually hearing? Because in fact, those graphs we were seeing were meaningless junk, not valid measurements at all. This isn't a bug or flaw in Plugin Doctor though, it's 100% user error. We're using a test called linear analysis, but we're trying to test distortion, which is, by definition, nonlinear. This test, which magically reveals the frequency response of a plugin almost instantly, assumes that the plugin being tested is linear. If you're testing a plugin with very subtle nonlinearities, then they probably won't mess up the results too much. You can test an analog modelled EQ and get proper results, so long as the test signal doesn't get too hot. But as soon as you introduce any significant extra harmonics, the results cease to mean anything at all, and we're no longer getting any useful information. I see this mistake over and again in YouTube videos, and this information really needs to be out there. You can't measure a nonlinearity with a test called linear analysis. Would it help if I explained how this test probably works under the hood? I don't know actually, but I think it helps me to know, so I'll press ahead and try to be as quick and concise as possible. Here's an impulse in Reaper. It's literally just one single full-scale sample with all others at 0. Now, here's a complex EQ shape in Pro Q3 using multiple bands. I'm going to run that impulse through this EQ setting and render the result, which looks like this. This is the impulse response. Yes, that's right, the impulse response, capital letters, the IR. If I trim this file and load it into Reaper's stock IR loader called Reverb, it sounds like this. For comparison, the original Pro Q3 setting sounds like this. The impulse response is that complex EQ setting, and if we want a graph of the frequency response, we can run a Fourier transform. Here's an application called Room EQ Wizard, which allows you to load an IR and analyze it. And there's that complex EQ shape we started with. So what Plugin Doctor is almost certainly doing is feeding the plugin a series of single sample spikes, like the one I used, then running a fast Fourier transform for the outputs. It's grabbing a series of impulse responses, in other words, and we all know that IRs are linear. They can do reverb very well. They can reproduce the EQ characteristics of a guitar speaker cabinet quite convincingly, but they can't do distortion at all. So, okay then, smarty pants, I hear you ask, how should you measure a nonlinear plugin's frequency response? Let's switch to the Hammerstein tab. There is a more interesting test to be run here, but before I show you that, let's create an accurate version of what we were attempting to do with the linear analysis. I'm going to set the order at the top right to 2. Actually, 1 would be better, but it doesn't matter because next we're going to zoom and scroll the vertical scale so that this first harmonic is roughly halfway up, and we have a reasonable 30 or so dB of range between the top and bottom of the scale. The first harmonic shown here, that's the fundamental frequency, same as the input signal. So we're now seeing the actual frequency response as I change the gain structure through the plugin. This is rather less exciting, but it matches much better what my ears are telling me. Driving the plugin harder doesn't really change the frequency response, like actually EQing the signal would. It just adds extra harmonics. So given that it's the added harmonics that are of interest in this case, how do we measure those? Let's switch to the harmonic analysis tab. And for now, I'm analysing an instance of Pro Q3, which is currently in bypass. This test is similar to the linear analysis in the sense that we're looking at a Fourier transform showing the frequency response. But this time the input signal isn't a burst of all frequencies, which is what the impulse amounted to. Rather, it's a single constant sine wave at a single constant frequency, which you can set with the slider at the top. In fact, you don't really need Plugin Doctor to run a test like this. Just generate a clean sine wave with a test tone plugin or a synth, and view the results on any spectrum analyzer. And that suddenly looks a little worrying. Is that noise I see there at the bottom? I thought Q3 was supposed to be super clean. I want my money back. Well, the important thing here is to be aware of the vertical scale. Plugin Doctor is showing content 200 dB below full scale. Yes, Q3 is introducing some noise, but I guarantee it's never going to be audible, never going to be an issue, whatever you do to the signal afterwards. Let's have a little perspective. This is 16-bit dither noise, which fills all the silences on a CD and is totally inaudible at any normal listening levels. And here's a noise floor typical of a high-end tape machine running Dolby noise reduction. Seriously, that stuff down at -180 or wherever that Q3 is adding, you don't need to worry about that. A quick side note. Apparently lots of people are very concerned to know what the internal bit depth of a plugin is, and I gather the FabFilter team have been fielding many requests for very high internal resolution above 100 bits. But you know that won't make it sound any better, right? Perhaps it will reduce that already negligible noise floor even further. Wouldn't you rather be able to load more instances instead? Really, internal bit depth is not something that the end user should have to concern themselves with. It's up to the plugin developer to ensure that their algorithms are calculated with enough precision to provide stable filters and a negligible noise floor, because we've already got enough to think about getting our mixes together. If a plugin gives you options to change the internal bit depth, ask yourself why it's not already running with enough precision to work properly. And if it is already working properly, why is it inviting you to waste resources by increasing the precision higher than is optimal? Note that these arguments don't apply to oversampling, as the amount of oversampling required depends on the nature of the input signal and its gain level, as well as the plugin's own settings, and can't really be set optimally by the developer in advance. Anyway, enough about the noise, and there's nothing else here. So let's try another plugin. Here's the Neve-style preamp and EQ we tested earlier, and now we're seeing added harmonics. Let's set the test tone to 100 Hz to make the maths easy, and we can now easily identify which harmonics are being added. This one is at 200 Hz, so that's the second harmonic. Next up is 400 Hz, the fourth harmonic. Then 600, 800, 1K, 6th, 8th and 10th harmonics respectively. Notice that the odd harmonics are missing. Even harmonics tend to sound sweeter than odd harmonics, suggesting this preamp model will add a subtle sweetening effect to the signal. But once again, let's pay attention to the vertical scale. With default unity gain settings, the second harmonic is about 60 dB lower in level than the original signal, so we can expect that sweetening to be quite subtle. Let's try switching from the line input to the mic input. The even harmonics get a bit louder, but more importantly, the odd harmonics now join the party as well, giving us more or less the complete harmonic series. We could expect this sine wave to gain just a little bit of the brightness you would expect from a sawtooth wave. Okay, let's try boosting the input gain and cutting the output gain to compensate. There's no doubt these harmonics will be audible now. Notice that the relative levels of the harmonics have changed as well. The third harmonic is now more prominent, suggesting a tiny bit more of a hollow square wave character might be present. Okay, now let's try adjusting the actual EQ, which has so far remained flat. If I boost the low shelf, we see the lower harmonics increase in level, but nothing much changes otherwise. Likewise, if I cut instead, the harmonics drop in level, but the pattern of harmonics doesn't really change. This suggests to me that what we have here is a non-linear preamp stage, followed by a linear or mostly linear EQ. There's nothing wrong with that, but it's not the same as a non-linear filter. Here's Volcano 3 running a low shelving band set to the hard style, but set flat for now with no boost or cut. There are harmonics, but they're quite subtle, so let's turn up the drive knob and push it harder. They're still nowhere near as prominent as the other EQ plugin, but never mind, let's try adding some EQ boost with the peak knob. And look what happens to the harmonics now. They dramatically increase in level compared to the fundamental, but also their relative levels change, and different patterns of harmonics emerge as I boost harder. Perhaps even more usefully, this also works when cutting, but the resulting pattern of harmonics is quite different compared to boosting. And you can also expect to get different patterns of harmonics from each of the different filter styles. Clearly, running colourful, saturating EQ or filters in Volcano 3 is not the same as running an instance of Saturn followed by Pro Q3 and won't give you the same results. That doesn't necessarily mean it's better, of course, but fortunately they're not exclusive. You'll often find me running all three plugins on one channel. But you may be wondering at this stage, what about all the other frequencies? We can see what happens to a 100 Hz test tone, but we can't assume that other frequencies will be affected the same way. Do we have to laboriously set our test tone to incrementally higher frequencies to get a proper picture of how a distortion will behave with a full range signal? Well, yes and no. That is what needs to be done, but that's essentially what the Hammerstein test does, which removes the laborious part and also provides a better way to view all the results. This time I'm going to stick with the default 6th order setting at the top right to view the first 6 harmonics. But you might still have to adjust the vertical scale to get the first harmonic visible at the top, or else adjust the output gain of the plugin to bring it below full scale. Now we can see the first harmonic at the top with the low shelf boost clearly visible, and below it we see a graph of each added harmonic, colour-coded according to the key at the top right. That's much better, right? Let's check that line input setting again. With unity input gain, we do indeed have mostly even harmonics. But this time we can see that the odd harmonics recover slightly at the low and high extremes. But if I add more input gain, the odd harmonics become much more prominent. If I switch to the mic input, the odd harmonics overtake the even for the whole spectrum. Looking at different types of distortion in the Hammerstein tab can be illuminating. Here's Saturn II, running the warm transformer style with the drive set low, and we see mostly some prominent odd harmonics in the low frequencies. But if I set the drive higher, suddenly we're saturating the transformer and getting a ton of higher harmonics, both even and odd. Contrast this with the warm tube style, which is all about that warm, sweet-sounding second harmonic. However, as interesting as it is looking at these graphs, it has to be acknowledged that they don't really help that much when it comes to mixing. Here, for example, is a Volcano 3 running a tube-style high-pass filter plus a hard-style low-pass filter, both set with quite a lot of drive. That's a very interesting pattern of harmonics we're seeing here, but it doesn't help you to understand that this setting is probably going to sound amazing on your electric guitar parts. Seriously, try it. So by all means, analyse your distortion plugins like this if it floats your boat. But don't forget to also listen to them on a variety of sources and in context, because that's the only way to properly understand the psychoacoustic effect those added harmonics will cause inside a human brain. Alright, there's an elephant in the room called aliasing, and I'm not going to ignore it any longer. But I've already covered the topic before, so I won't repeat myself. There's a Samplerates video over on the FabFilter channel, which I'll pop up a card for, and also an oversampling video here on this channel. Links below. I'm just going to focus on testing for aliasing. You might need some kind of audio editor for this test, because the first step is to generate a sine wave sweep. That's easy in an editor like SoundForge, or in this case, I'm using Acoustica from Acon Digital. It doesn't particularly matter what length of sweep you go for, but 2 or 3 seconds is enough for the purpose. It also doesn't hugely matter what gain settings you choose, as you'll be able to adjust that afterwards anyway, but I generally go for -20 dB. The choice of linear or exponential does matter, however. The linear sweep increases in frequency at a constant rate in hertz, while the exponential sweep increases at a constant rate in pitch, measured in semitones or octaves. Either kind can work for this test, but aliasing is easier to see and understand if you use a linear sweep and then view it with a linear analyzer. Okay, now you can save this file for future reference. And the next tool we need is a spectral analyzer, like this one in Acoustica. Now we can see that the sine wave sweeps up in pitch. But why is it curved? Well, we need to change the vertical scale. I'll set it to linear to match the sweep. And now it's a straight diagonal line. There are various different applications you could use for this spectral analysis. I've got a copy of Wavelab that can do it, or there's Isotope RX, which is a popular choice, I believe. But as I work mostly in Reaper, it's usually most convenient for me to view the results right there in Reaper. But again, with the vertical scale set totally linear, so the sweep is a straight line. Now we're ready to run a test. Simply bounce this sweep through the plugin you want to test. Then check the result with your spectral editor again. You see this fan of upward sweeping lines we've now got at the start of the file. Those are added harmonics. The second harmonic here is always twice the frequency of the first harmonic, so with a linear scale like this, it seems to climb faster. This is all perfectly normal and unremarkable. What we're interested in is what happens when those harmonics hit the Nyquist limit at the top of the scale. They should just stop. That's what analog distortion would do. But in fact, they reflect back down again and sweep down in frequency until they reach 0, at which point they reflect back up again, and so on. That's aliasing. Incidentally, here's how it looks if you do this test with an exponential sweep and view it on a logarithmic scale. The added harmonics now run parallel to the original sweep, which is fine, but when they reflect back down at Nyquist, the curve turns upside down, so the log scale no longer corrects the exponential sweep, and the aliasing gets this strange downward curve. This still works fine as a test. I just think it's clearer and easier to understand in the linear version. Anyway, if I turn on oversampling, those reflections disappear, and we get a much cleaner, more authentically analog response. Different developers may have different opinions as to the optimum settings for the anti-aliasing filters. Sometimes the harmonics will fade out just before they reach the Nyquist limit, indicating a slightly lower filter cutoff. Sometimes you'll see little stubs of reflections that fade out before they get back down below 20 kHz, indicating a slightly higher filter cutoff. Which approach is best is largely a matter of opinion. The main thing is that aliasing doesn't get into the audible range, and these examples have achieved that admirably. This is what proper oversampling looks like. The next question might be, are these up and down sampling filters linear phase or minimum phase? Actually, you get a big hint from the plugin's latency. If it increases significantly when oversampling is enabled, that suggests linear phase. A more definitive test, however, would be to measure the phase response in Plugin Doctor. Here's Saturn 2, but with the mix slider set all dry, so it's not actually doing anything at all. If I switch to show phase, still just a flat line, nothing happening. Let's turn on oversampling. And now there's a load of phase shift at the high end. This actually isn't anything to be scared of. Phase shift is nearly always inaudible, even when it's quite severe like this. But sometimes, with some sources, it may be an issue, or you may want to run this setting in parallel with the dry signal, in which case you can turn on linear phase mode, and the phase is nicely flat again. Okay, now we're talking about phase shift again, so let's talk about measuring phase shift. Here's that all-pass filter again that we used earlier. The frequency response shows as flat in Plugin Doctor, but the phase plot definitely isn't. First of all, let's explain this apparent sharp discontinuity at the cutoff frequency. This actually represents 180 degrees phase shift, and it isn't really a discontinuity at all. In fact, the phase smoothly rotates through 180 degrees and back round the other side of the phase circle. But because of the way we're representing that on the graph, the line disappears off the top and reappears at the bottom again. But it's quite useful, really. That vertical line shows us precisely which frequency will be rotated by exactly 180 degrees, and we can confirm that it is indeed exactly the frequency we've set for the filter cutoff. So let's see what kind of phase shift we get from typical EQ-type filters. Here's a bell-shaped boost, and here's the resulting phase shift. Notice that the frequency I'm boosting is actually at 0 phase, and the phase shift happens either side. In fact, the phase shift is greatest where the gradient is steepest on the frequency response. Notice also that the phase shift is both positive and negative. That means it's not delaying those frequencies, as you'll often be told. We're in zero latency mode, so negative delay isn't an option. It's phase shift, which isn't the same. If I cut instead of boost, the phase plot stays the same, except the positive phase shift becomes negative, and vice versa. Another thing to notice, this is quite a significant EQ cut, but the phase shift still doesn't get anywhere near wrapping around at 180 degrees like the all-pass filter did. Mixing this EQ'd signal with the dry signal isn't going to cause any drastic cancellation or weird coloration of the sound. In practice, it just slightly changes the width of the cut or boost you're applying. So if you're one of those people that's scared to EQ individual channels of a multi-mic'd drum kit, or who uses linear phase EQs to avoid the phase issues you've been warned about, stop it. There's nothing to be scared of from normal bell-shaped EQ moves, or indeed from shelving filters, which exhibit similarly subtle and gentle phase shift. Phase shift gets more extreme with high or low-pass filters. We do get to 180 degrees of phase shift this time, but that happens beyond the cutoff frequency, where the signal is attenuated significantly, so this may not cause serious problems, even when mixed with the dry signal. I've made a whole video about parallel high and low-pass filters, though, so I'll just refer you to that if you want to know more. Anyway, there are 2 points I want to make about phase. First of all, it's kind of a scary concept at first, this invisible, inaudible thing that can apparently ruin your mix. Holy cow. No wonder people are apprehensive. And unfortunately, that fear gets exploited by some marketing types. This EQ has naturally gentler phase shift, they'll tell you, so you can EQ your sounds without messing up the phase. I picked on Pulsar for this recently, who used this line in their marketing for Massive. But just to show they're far from alone, here's the blurb for the Marg EQ we looked at earlier.
The Marg Audio EQ4's unique design allows for exceptionally low phase shift across, helping maintain the integrity of your mix's original sound while enhancing the airy frequencies.
Let's check that, shall we? Here's a mid-boost from the Marg. And here's the same curve matched as closely as possible with Pro Q3. Let's check the phase. It's substantially the same. Of course, there are minor differences due to the Marg box tone, But the EQ itself isn't noticeably gentler in its phase shift. Let's try the famous air band. Again, matched as closely as I can with Q3. And again, the phase shift is basically the same. That's because EQ is phase shift. That's just how it works. Doesn't matter if it's digital, analog, active, passive, acoustic, whatever. Real life is minimum phase, and the phase shift we see here is just a natural consequence of the change in frequency response. The only way in which this EQ exhibits exceptionally low phase shift is by not providing any option to make the EQ any sharper or steeper. Now, it's important to note that this isn't a criticism of this plugin. I'm not saying the plugin sounds bad because it causes phase shift, nothing of the sort. My problem is with marketing that makes claims that fundamentally don't make sense, and which perpetuates the myth that phase shift is evil and scary. That myth stems from ignorance and insecurity, and I wish plugin developers would stop promoting it. Okay, my second point about phase shift. It's a perennial question, which the FabFilter team get asked regularly, I gather, and which constantly pops up on forums and social media. Why does this EQ cut / high-pass filter make my mix get louder? There's a mistake built into the question, in fact, which I'll demonstrate with a sawtooth wave, and I'm showing both the peak and the RMS levels on this meter. Now I'll add a high-pass filter from Pro Q3 and tune it so that it just starts to shave off the lowest fundamental. We definitely haven't made this louder, have we? And indeed, there's little difference on the RMS meter. But the peak levels are way higher with the filter switched in. So it's not the loudness that increases when you add a high-pass filter or a shelving cut. It's only the peak levels. But why does it happen? Well, it's our friend phase shift again. I can prove that by switching to linear phase mode instead. No real effect on the peak levels anymore. But explaining what's actually going on requires me to do a bit more work. Let's look at that sawtooth wave on the analyzer again, and notice it's composed of a load of separate harmonics. Each of these harmonics is just a separate sine wave at integer multiples of the fundamental frequency. If I take a steep low-pass filter and filter out all the harmonics above the first, we're left with just a sine wave. But we can also go the other way and create a sawtooth wave additively by adding up a set of sine waves with the correct frequency and gain, and, importantly, phase. Here's a sine wave at 100 Hz. That's the fundamental. Now here's another sine wave at 200 Hz, twice the fundamental frequency, and also half the amplitude, so 6 dB quieter than the fundamental. When we add this in, the combined waveform gets skewed over to one side slightly. Still doesn't look much like a sawtooth, though. So let's add another 300 Hz and 1/3 of the amplitude, 400 Hz and 1/4 of the amplitude, 500 Hz, 600 Hz, and so on. And we're starting to see that the more harmonics I add, the closer we get to a sawtooth in shape. A theoretically perfect sawtooth has harmonics extending to infinity, but that never happens in practice, of course. A perfect digital sawtooth will have harmonics extending up to the Nyquist limit at half the sample rate, and absolutely nothing beyond that, because it will reflect down as aliasing if so. That's not our concern today, however. Instead, we're trying to explain the increase in peak levels caused by phase shift. Now, all these sine waves are currently neatly aligned, starting at 0 phase, and they stay locked in relative phase because they're all at integer multiples of the same frequency. That's why they add up to create a neat, orderly sawtooth shape. Now notice what happens if I slide the first sine wave, the low fundamental first harmonic, left or right to change its phase. We get a dramatic change in the waveform. No more neat sawtooth shape. And more importantly, with some phase settings, the maximum amplitude of the second harmonic now coincides with the maximum amplitude of the first harmonic, and the sum of the two increases as a result. Of course, your fully mixed track that you've already limited to full scale is more complex than a sawtooth wave, but it's still composed of many individual sine waves, and when you shift the phase of some of them but not others, they all start to add up differently. The peak levels change, and suddenly your mix is clipping red. Okay, then what's the solution? Well, you could switch to linear phase mode instead, but there's a much better solution really. Do all your filtering and EQing before the limiter, not afterwards. But, you might object, that means you'll be hitting the limiter harder with higher peak levels, right? Well, not necessarily. Some of the peaks might get higher in level after filtering or EQing. They're the ones you notice when you EQ after the limiter. But equally, some of them might get lower. No one ever notices or cares when that happens, but it's really just as likely. If you have no option but to EQ a file that's already been limited, I suggest you start by turning it down. Give yourself some working headroom so you can EQ as necessary without getting red lights. Then you can use another limiter to bring it back up to your target level and deal with any rogue peaks you might have created. Okay, so now I've mentioned a limiter. So how do you go about measuring dynamics processes such as limiters or compressors? Let's start with a question I fielded recently.
I checked ProL2 in Plugin Doctor, and my sine wave test tone gets loads of harmonics. I thought ProL2 was supposed to be transparent. What's going on?
There's a couple of mistakes here. First of all, transparent is a rather complex and subjective criteria and definitely doesn't equate to a simple measurement of how much distortion is added. When brick wall limiting, the trade-off is essentially between distortion and pumping, and the former will often be subjectively more transparent than the latter, especially if most of that distortion happens very briefly just after a transient. And there's the second reason this test is flawed. One of the most important criteria for a brick wall limiter is the way it handles transients. Perhaps the most important criteria, as in my opinion, transients should normally be the only part of your audio that ever hits the limiter threshold. And where are the transients in this sine wave test tone? It's just a steady state. This is not a signal that any limiter will ever be presented with in real life. How do you expect to measure the limiter's transparency with this? Really, if ProL2 is unusually transparent, it's pretty much entirely down to clever program dependency. The FabFilter guys have found ingenious ways to disguise the gain modulation and make it as unnoticeable as possible. How do you measure that? Well, short of a scientific definition of what transparent means when it comes to brick wall limiting, you just have to listen to it and come to a judgment. One advantage we have when comparing brick wall limiters, however, is that we tend not to have any analog modelled nonsense going on, and parameters tend to do precisely what they claim to do. Hence, it's usually very easy to match the threshold and gain settings for two different limiters, so you can shoot them out on equal terms. Of course, in most cases, you'll be setting an input gain and an output ceiling, but either way they're easy to match, and then you can tweak whatever other controls are available to see how good you can make it sound at that level. Things are trickier when comparing compressors. Now, if you're comparing two compressors that provide makeup gain controls calibrated in decibels, it's a fairly safe bet that both will match, and it's probably okay to just match the numbers. But what if one of the compressors you're testing is an 1176 or similar, like this 1178 from Pulsar, and you have input and output gain controls with a fixed threshold in between? You can't just match the output gains in that case, because the output gain of the 1178 needs to compensate for the input gain as well as the gain reduction. Granted, Pulsar have been helpful enough to provide dB calibrations for both gains, which you don't always get in this style of compressor, so it's not too hard to work out the total gain through the plugin. But then there's the next question: where's the threshold set, and how do I match that with the compressor I'm testing? Even if both compressors have an actual threshold control, you may still not be able to match the numbers. Here's an SSL-style bus compressor, which faithfully recreates an SSL bus compressor design quirk. When you change the ratio, the threshold changes to compensate. The idea is obviously that you can try different ratio settings without a huge change in the amount of gain reduction. In practice, I don't think it works so well and I'm not a fan. But the point is, even before taking any measurements at all, we know that with at least 2 of these ratio settings, the threshold will not actually be as displayed. But let's park those problems for the moment and assume that both the compressors you're testing have a conventional threshold control calibrated accurately. If both compressors have the same threshold ratio, because a ratio of 4:1 should in theory be the same everywhere, and makeup gain, we can say that at least they now both have the same transfer curves, right? Any remaining differences should now only be in attack and release behavior, right? Well, wrong. I'm going to have to turn to Plugin Doctor again to show this. Here's the transfer curve from T-Rack's compressor set to a 10:1 ratio. Note that this is an unusual style of compressor in that every different ratio setting results in a different style of compression with a different transfer curve. And here's Pro C2 with supposedly the same ratio settings. They're clearly not the same. C2 provides a knee shape control, but I can't find any setting that matches the shape of the compressor knee. Do these differences matter? Are these transfer curves close enough that they will sound the same? Well, in fact, that question may be academic, because any difficulty we have matching the transfer curves pales into insignificance when we start to consider attack and release behavior. Let's switch to the attack-release test. Here we have a sine wave, which I've set to 1 kHz. It starts at -20 dBFS for 1 second, then jumps up to full scale for another second, then returns to -20 for 2 seconds. If we set up our compressors to catch just that loud bit in the middle, we can see how the attack and release smoothing changes the envelope of this test signal. So here's the compressor response. Notice the powerful spike before the attack clamps down on the leading edge of that loud section. And the way the rest of the loud section continues to ramp down in level, as if a portion of the attack stage is much slower and is still responding a full second after the level change. The release looks like a very gentle curve, but if I slow it down, it starts to look like a 2-stage release, with some of the gain reduction releasing very quickly, but the rest holding on for much longer. And when you see how small the start of the release stage looks with a slower release setting, you start to appreciate that with the fastest release setting, which you get when you press the optical button, a significant portion of the release is happening almost instantly. Let's store this response using a nice contrasty colour. And let's see how closely we can match this with Pro C2. The Opto style would seem like a good starting point, but in fact it's nowhere near. If I try to match the initial attack spike, we don't get that slower, more gradual attack behaviour that the T-Rack's compressor provides. If I try to match that later part of the attack, well, now we're miles off with the initial spike. And I don't have any more luck with the release. It's just a totally different curve shape. While there are indeed a load of different compressor styles in C2, and they do look very different in this test, none of them managed to recreate this attack and release behaviour any better. Trust me, I tried them all. But hold on, you might say. What if both compressors have their attack and release controls calibrated in milliseconds? Surely you can just match the numbers in that case. But no, unfortunately not. There's no standard way to measure attack or release times for a start, so different compressors may be using different definitions that can't be directly compared. And even if they don't, the shape of the attack and release can vary enormously, as we've seen, and will affect the sound just as much. But it gets worse. I mentioned program dependency earlier when talking about limiters, but what do I mean by that? Well, it means the behaviour of the compressor or limiter depends on the input signal. Which seems kind of like a non-statement on the face of it. Yeah, of course it does. It turns it down when it gets too loud. Surely all dynamics processes are program dependent by definition. In a sense, yes they are, and program dependency is quite hard to pin down as a concept, as it can really mean anything. One possible implementation would be attack and or release stages that react more quickly to short transients than to slower dynamic changes. That's likely to be what happens if you enable an auto setting for attack or release. But equally, program dependency might mean precisely the opposite behavior. Or it could mean a change in the ratio depending on the ballistics of the input signal. Or it could mean the speed of the release depends on how long the signal spends above the threshold. Or perhaps the compressor reacts more slowly to lower frequencies than to higher frequencies. Basically, there's an infinite number of ways that a compressor or limiter can be program dependent, and even if you did manage to match their attack and release curves in a test like this, there's no guarantee that they will still behave the same way when presented with a real-world signal with more realistic dynamics. So what's the correct way to compare compressors then? Well, really, you just have to listen to them. So set them both up as close as you can in terms of ratio setting, then try to match them both in terms of how much gain reduction they're applying. This can be tricky in itself, as you can't always trust the gain reduction metering, especially in vintage-style analog modeled stuff. But if you can match the makeup gain setting accurately, you can then set the threshold so that the output loudness matches the compressor you're comparing it to. And you can then switch between them and listen to the differences, with your eyes closed if necessary. The good thing about this test is you can focus on the subjectively different feel you get from each compressor, and indeed how easily you can coax that feeling out of it. You might discover that hypothetical compressor X, with its myriad controls, is quite capable of accurately recreating all your vintage compressor models. But perhaps you might still prefer to reach for an 1176 when you want FET-style compression, because that sound is just there already, and you only have to worry about tweaking it to perfection. Now, you may be thinking, surely there are valid tests we can run on a compressor? We can check for aliasing, for example, right? Well, okay, let's start with a test tone at 100 Hz, and I'll squash it hard with Pro C2. With about 20 dB of gain reduction, we get quite a lot of added harmonics. Changing the compressor style changes the amount and pattern of harmonics. But other than the mastering style, which is hilariously clean, they all add significant harmonics. It's reasonable to conclude, therefore, that there'll be aliasing, unless this is oversampled by quite a lot. We could test that theory with the sweep test we did earlier when looking at distortion plugins, and the results look much the same as for a distortion or saturation effect. Has anyone spotted the problem yet? The test signal is a static sine wave in both tests, not a signal a compressor is ever likely to be presented with in real life. So these tests don't really mean very much. We've discovered that the mastering style seems to be supernaturally free of distortion, but that doesn't tell us what it actually sounds like in practice. So can we devise a more illuminating test? We could, for example, take some drums and find a compressor setting to test. Then route those drums to the sidechain input while running test tones through the main signal path. But actually, there's a much simpler option. We already know how to isolate the difference between compression with oversampling and compression without. We can just run a null test. With the quick proviso that this is only a viable option because the oversampling is linear phase. With minimum phase oversampling, any differences due to aliasing would likely be dwarfed by the huge phase differences, and we wouldn't learn anything. But let's double-check that with the control. Here's pink noise, running through an instance of C2 that's not doing anything at all. And the same noise through another instance with 4 times oversampling. Let's null them. And there's nothing left. apart from the expected differences right at the highest frequencies due to the anti-aliasing filters. So let's do the same thing, except with drums as the input signal, and with a healthy amount of squash. Here it is with oversampling. And here it is without. And here's the difference, according to the Null Test. Not much there, is there? It's largely dropped below my usual minus 100 dB don't care threshold. Let's dig a bit deeper. And there it is. If I crank the level by a lot, we can hear some little clicky noises. It's interesting that before I ran this test, I was reasonably sure I could hear a difference. I'm rather less confident now. But there is a way I could find out, definitively and scientifically, whether indeed I can hear any difference at all. It's another gold standard audio test, much like the double-blind randomized control trial that's the scientific standard for modern drug testing. That's what you do when you genuinely want to know if a drug really works or not. And likewise, if you want to know if a subtle difference in audio files is actually audible, you run an ABX test. Blind testing is strangely controversial in audio circles. Not surprisingly, the audiophile hi-fi buffs tend to reject it. You can't listen properly under test conditions, they will tell you, therefore the test is not valid. More surprisingly, I've seen substantially the same argument coming from well-known mastering engineers that I otherwise admire and respect. The choice of dither is absolutely critical, they will have you believe, before admitting that they can't pick out the different dithers in a blind test. I would argue that the listener goes a step beyond double-blind to triple-blind. They don't know what type of dither was used, no one else in the room knows, and furthermore, no one cares either. If a difference disappears in a blind test, then it's not an important difference. You can't really argue with that, right? So here's how an ABX test works. You have file A, which you can play back as many times as you like. You have file B, which you can also preview as many times as you like. And then you have file X, which is one of those two. Again, you can preview it freely and compare it to A and B until you feel certain which one it is. State your opinion, then try again with another randomly chosen hex file. You need to repeat this test quite a few times to get a statistically significant result, maybe 15 or 20 times minimum. And don't peek at the results while you're doing it. Wait till you've run all the tests, then see how many you chose correctly. If it's 100% correct or close, then yes, you can clearly hear that difference and pick it out accurately. If it's close to 50%, well, sorry, you were just guessing. And if you get a result around 75%, then, assuming you ran enough tests to exclude blind luck as a factor, that suggests that there is a subtle difference, but it's quite hard to hear. Note that it's absolutely critical the two files are properly level matched for a test like this. Even 1/10 of a dB difference is enough to make one file sound better than the other. Note, however, that the ABX test doesn't require any subjective judgments about which sounds better. This is not a subjective which file sounds better test. It's a scientific, objective test of can you actually hear the difference? And logically, it should be the next step after a null test confirms that a difference genuinely exists. The follow-up question is surely, okay then, but does it matter? The problem is, while there is software available to make ABX testing as easy as possible, it can't remove the need to repeat the test many times to get a meaningful result, and frankly, it's not very much fun. I'd rather be mixing a song, personally. So I'm going to finish up by telling you the best way to decide if a plugin is worth using or not in the real world. Toggle bypass in context with your mix, with proper gain structure of course, so it's not just getting louder, and if necessary with the interface hidden or with your eyes closed. Does the mix sound worse with it bypassed? Is the mix a bit closer to being finished when you enable it again? If yes, bank that difference and move on. It's the only one that matters. Okay, that's all, finally. Congratulations to anyone who made it this far, and thanks for watching.